Hey, welcome back to Fat Mama Physics. This is the third video going over examples that have to do with normal force. In this example and the example following, we will talk about bathroom scales. So let's get down to business. You have a bathroom scale. Oh, you take a bathroom scale to the moon to measure your weight. On the moon, you read this 12.5 kilos. It's not going to have so much significance. I'm not going to label it now. If the acceleration due to gravity on the moon is 1.6 meters per second squared, which is one-sixth of the gravity we have on Earth, calculate your weight on Earth. So we want the weight, Fg, and we want that one on Earth. We do know that the acceleration due to gravity on Earth is 9.81 meters per second squared. And to calculate your weight on Earth, we need your mass times g on Earth. We have g, we don't know your mass. Is that your mass, 12.5 kilos? I don't know. You read that one on the moon, so maybe it's not that accurate. You might be thinking, oh, just multiply this mass by 6 because you just have to get it to the moon. Okay, you're on the right track. Let's go over things step by step. I also didn't tell you that in this question that the moon is 1/6 gravity on Earth, which means if you get a different planet with a different acceleration, that may not be the case where you can just do that. Okay, so let's talk about bathroom scales a little bit more before we move on. So I drew this person here, and let's say he's on the moon, so that the acceleration's weight is going to be that what he would read on the moon. Because he's sitting on the scale must exert an equal and opposite force on him, which we know that's the normal force. So when the question says it reads 12.5 kilograms, what does it actually mean? Is it his actual weight? Does it have to do with his weight? Because we know his weight on the moon is his actual mass times the acceleration due to gravity that's on the moon, which we know is 1.6. This m would be his actual mass. So where does this number come in to play? To really talk about this, we need to have a basic idea how a bathroom scale works, or at least a very basic kind, where they have a spring attached here, and the more you depress the scale, the more you're going to depress the spring downwards, which then will show a reading on your dial. So the more you're pressing down on it, the more it will press back at you. So that means whatever your scale is reading has some direct relationship with your normal force. That's right. The 12.5 kilograms has to do with your normal force. But the normal force is a force. It's not a mass reading, kilograms. Well, that's because your bathroom scales are designed so the user can read it and understand it to a certain point. If all the bathroom scales read newtons, no one would understand anything about their mass, right? And the other thing about bathroom scales, they are designed to work on Earth. Which means when you step on the scale, it presses down the spring and measures a normal force, and it must spit out a number for the commoner, such as you and us and everyone else, the public, to be able to understand, which is in kilograms. So how do we convert a force to mass? There has to be some division of a acceleration value. And since this bathroom scale is designed to function on Earth, this bathroom scale does something internally by taking this force reading, dividing it by 9.81, which is the acceleration due to gravity on Earth, which then spits back a number out at us. And that is just what the bathroom scale does. Because you would read because your Fn would be smaller on the moon, dividing it by gravity, dividing by 9.81 is going to give you a smaller mass reading. So in fact, we need to take this 12.5 and multiply it by 9.81 to get the actual normal force that you would experience on the moon. So let's do that right now. Keep in mind, this is not a permanent equation for Fn. It's just by situation. This just because of bathroom scales, this is what we had to do. Now that we have Fn, we can probably use that to figure out the person's mass on the moon, given that these two are equal when acceleration is 0. So Fn on the moon is going to be equal to his Fg on the moon. Fg on the moon is here, so I can just substitute all of this in. I get where g is 1.6 as given in the problem, so let's put all these values into the problem. Isolating for mass by dividing by both sides by 1.6. I get the mass is 776.6 ... kilograms, which we will need to calculate his weight on Earth. So multiplying this by 9.81, which is acceleration due to gravity on Earth, we get 7518. 1.8. Rounding this to 2 sig figs, we get 750 newtons. Now the 750 newtons as a weight is much more than his weight on the moon. Now I did all of these steps so that you could use the same modeling technique for a second problem, which I have here on Proxima Centauri b, a nearby exoplanet. So let me go through this problem first to make sure you understand what's happening. So if you don't know what an exoplanet is, it's a planet that is outside of our solar system, probably revolving around some other star. In fact, this one is revolving around a red dwarf. That is, I forgot how many light years away. I think it's 40 or something. Anyway, it's really, really far away. The surface gravity of this planet is 10.8 meters per second squared, which is roughly 1.1 Gs. What this means, if you've never seen this language before, 1.1 Gs just means 1.1 times the gravity that's on Earth, 9.81 meters per second squared. That's what 1.1 Gs means. So if you're experiencing, some of you might hear the word, oh, I'm experiencing 3 Gs. That means you're experiencing a whole whack ton of weight because you're feeling Earth's gravity 3 times than what it is, 9.81. You are one of the lucky individuals to win a trip to this planet to live there for a lifetime. If you don't even want to do that, you brought a bathroom scale with you from Earth. Okay, so it's a bathroom scale designed to work on Earth. Curious how your weight will change on this new planet. So your weight on Earth is 699 newtons. What would be your kilogram reading on your bathroom scale when you are on the surface of Proxima Centauri b? Okay, so you take your bathroom scale onto Proxima Centauri b. What would you read on that scale? Assuming this scale read in kilograms. That is what the question is asking for. So this is kind of using the problem before a little bit to help you with this one. Good time to pause your video and I will play the solutions on Fast Play. Okay, and here I go. First, let's record a few values that we found in this problem. The gravity on Proxima Centauri b is 10.8 meters per second squared. We also know the weight of the person on Earth, which is 699 newtons. Let's draw a free body diagram of this person on this exoplanet. First, we have him standing on the scale, his weight, and the normal force that the bathroom scale is exerting on him. Remember that in order to find the mass reading on the scale, we need to take the normal force divided by 9.81 because his bathroom scale thinks it's on Earth where the gravity is 9.81. And to do that, we need the person's weight and we need the mass if we need the weight. And the way to find the mass is to go over to Earth using the weight on Earth to calculate the person's mass. Dividing by 9.81, we get the mass is 71 roughly kilograms. Without doing any rounding, let's plug that in on the other side to find the weight of the person on this new exoplanet. Timesing by 10.8 meters per second squared, we get 769-ish newtons, which we now need to divide by 9.81 to get the bathroom scale reading on Proxima Centauri b. And dividing by 9.81, we get 78 kilograms, which is larger than the reading we would have on Earth. Okay, so in the solutions here, we needed to find the reading on the bathroom scale on this new exoplanet. And to do that, we needed to find the person's normal force first, divide that by 9.81 to get a bathroom scale reading. And that scaled back to us needing the actual mass of the person by using his weight on Earth. And our final answer that we got was 78 kilograms, which indeed is greater than his actual mass. So that makes sense, because if you did take this Braatham scale to Proxima Centauri with a stronger gravitational force, you would get a larger reading on your scale. And of course, it is not your actual mass, but it would be what you would read. So hopefully you learned something from this video. Good luck on the rest of your practices. Thank you for watching this video. Tune in next time on Fat Mama Physics. Signing out.